So welcome to lecture number 10. So today's topic is still variance reduction. Today we'll speak about two other methods, which are stratification and importance sampling. Okay, but let's recall our main goal. So we are still speaking about Monte Carlo quadrature. So we are given a function from Rd to R and an Rd valued random variable x. And we still want to know this expectation here. So theta is the expectation of f of x. The classical MC estimator is, okay, let's have n IID copies of x, so x1 up to xn IID copies of xn, and then plug them into f and average. And the main idea, or the basic idea of variance reduction is, okay, we do not use f of x, but we replace f of x by a simulated variable z, which has the same unknown mean which we want to know. And then apply classical MC on this new representation. Okay, so we always speak about variance reduction, but it should be actually variance cost reduction. So I showed you last lecture, the thing which we want to minimize is VC of z, which is the cost of z times the variance of z, because this is the main quantity if you express the mean squared error in terms of the computational budget. Then we computed last lecture that the mean squared error is 1 over d times the cost of z times the variance of z plus a small O of 1 quantity. So the smaller VCZ, the better. Okay. And now what's stratification? That's our next section. And each variance reduction method has a slogan, has a motto, as I told you, and stratification, here you can use the slogan, good allocation of randomness. And we will again use that our random variable has a density with respect to the Lebesgue measure, so we are d-dimensional, so we have a density with respect to the d-dimensional Lebesgue measure, and we write p for this density. And we also need as a notation the support of this density, so curly s is the support of p, and these are all the x's such that p of x is greater than 0. Okay, that's the setup. A random variable with a density with respect to the Lebesgue measure, support of this density is curly s. And then stratification requires 4 steps. So the first step is to decompose the support of the density. So we write S as a disjoint union of the set Sj's, so it's always curly Sj, and as the Sj's are subsets of S clearly, and they are disjoint, and of course they are measurable. So we decompose our support. In 1D you can think about intervals, so here is the support of S, and then you can cut down the support of S in these intervals here, and in this illustration they all have the same length, but that does not need to be the case in general. So we decompose our support into m disjoint and measurable sets. Okay, that's step 1. And step 2 is to compute these normalization factors here. So why is this decomposition of the support a good idea? The slogan was to have a good allocation of randomness, and this decomposition here is done for sampling conditionally on Sj. And for this we need these normalization factors, or normalizing factors. So Aj is the probability that x takes value in Sj, and because x has a density with respect to the Lebesgue measure, these probabilities are just the integral over Sj with respect to the density. And then having these factors Aj, we can write down the conditional distribution which we need, which is a distribution of x under the condition x takes values in Sj. And this distribution here has again a Lebesgue density, Pj, and Pj of x is just P of x divided by Aj if x is an Sj and 0 else. So if we are an Sj, we can take the original density and have to normalize it by alpha j, and otherwise the density is 0 because, well, it can take only values in Sj, this conditional distribution here. Okay, for decomposition of the support, normalizing factors, and what's the next step? The next step is to choose the number of repetitions for each stratum. So what is a stratum? Well, the SJs are called stratum. So we decompose, then we think about sampling conditional on the SJs, and in the next step we need to think about how many repetitions we need to assign for each stratum. Okay, and after these 3 steps we can finally write down the stratified estimator, and the stratified estimator is given by this expression here. So let's first look at the inner part. Well, the inner part are just the classical Monte Carlo estimators for each stratum. So the xji's are IID copies of xj, and we take nj of them and plug them into f and average, and after that we run over all strata and average with additional weight alpha j here. Okay, and that's the stratified estimator. Break down everything into stratas, sample conditionally, use on each stratum the classical MC estimator, and then average again. Okay, and which properties does a stratified estimator have? So first of all, the stratified estimator is still unbiased. So on average we get our theta. And for the variance we have the following expression here in terms of the variance of f of xj. So the variance of the stratified estimator is the sum over the strata, and then we have alpha j squared divided by nj, and then the variance of f of xj. And here for completeness I have written out the variance of xj. Well, it's this integral here over sj, f of x squared times pj dx, and then, well, we subtract the conditional mean squared, which is an integral over sj, f of x pjx dx, and then the squared. Okay, and well, this can be really obtained by elementary calculations, or standard calculations we are always doing. Okay, so we are unbiased, and we have this variance here for this expression here for the variance. And the question is now, when is this variance here smaller than the variance of the standard estimator? And it turns out that even for really simple stratification strategies, you can obtain a smaller variance than the one for the standard estimator. And the simple stratification scheme is a so-called proportional allocation. Here we start with an initial budget n. So we call that AJs are the probabilities that x takes values in Sj. And here we just take for each stratum n times AJ, numbers of repetitions, and because this n times aj does not need to be a natural number, we round up to the next integers. So proportional means here choose the numbers of repetitions proportional to the probabilities aj. Okay, and if we pick the nj's in this way and sum them up, we get n star. N star may be larger than n, but n star and n can differ at most by capital M. Okay, and with this stratified estimator has a smaller variance than the standard estimator. So that's the statement we can make about the variance. Well, for the computational cost, we cannot make a general statement. The computational cost depends really heavily on the cost of sampling from the conditional distribution. Sometimes it's simple, sometimes it's not simple. Okay, I would like to prove this lemma. And we need a tool from analysis for the proof, which is Jensen's inequality, one of the standard inequalities in analysis. So what we are having here, so A1 up to AM are numbers between 0 and 1, and if you sum them up you get 1. So you see the AIs are just probabilities, and all these probabilities add up to 1. And x is a vector in R capital M, and then we're having the following inequality. Well, if we multiply the AI and the xi, sum them up and square them, this is less or equal than squaring the xi's first, multiplying them with AI and then summing up. And this version of Jensen's inequality we need for the proof of lemma 10.2. Okay. Okay, now the proof of lemma 10.2. So it has this proof has two steps. And the first step is just to rewrite the variance of the standard estimator and then use Jensen's inequality. Okay, so what's the variance of the standard estimator? Well, we have seen this many times. The variance of the standard estimator is the variance of f of x divided by n. Okay, let's now look at the variance of f of x in a bit more detail. So we have a density, so we can write the variance in this way. Integral over s f of x squared px minus the square of this integral here, and this integral is just the expectation of f of x. Okay, so we have written the variance in this form, and then we use now the strata. Okay, the first integral here we can cut down in the integrals over the Sj. We just need to sum up over all of them, and for the integral inside the square we are doing the same. So integral of f of x px is rewritten as sum over j from 1 to n, integral over sj fx px. Okay, it's just rewriting. In the next step, instead of p, we are using now the conditional densities. We can do this because we are integrating now over the sj's. So instead of writing the integral over sj and with p, we now write the integral still over sj, but now with pj. Of course, pj is px divided by aj. So we have to plug in this aj here to have everything still correct. So we are doing this here, and also for the second part here. So replace p by pj and plug in the aj's to have everything still correct. Okay, so it's rewriting using the conditional densities and the strata. So here is the expression again we have obtained for the variance of f of x, and now you see here something blue and something red. So now we are in the position to apply Jensen's inequality. So the aj's are the probabilities. Well, they are probabilities. They're summing up to 1, and the red thing, this will be our xj's. Okay, and Jensen's inequality tells us sum up the blue times the red squared, and this is less than squaring the red stuff first, multiplying this with the blue stuff, and then summing up. Okay, so because this is less or equal than this, this expression here is less or equal than the variance of f of x. So the variance of f of x is greater or equal than the sum over the aj's, sj f of x squared pj x dx minus sum over the j's, aj's, and integral sj f of x pj x dx and the squared. So we have in fact obtained a lower bound for the variance of the standard estimator. Okay, and you see this is a bit of a backward proof. Now we compare with the lemma, with the variance which we obtained for the stratified estimator in lemma 10.1. And here we obtain this expression. So the variance of the stratified estimator is the sum over the j's, aj squared divided by nj, and here we have the integral sj f of x squared pj x dx minus the integral minus the squared integral sj f of x pj x dx. Okay, and if we look at this now, what can we see? Now not much. Now we need to use the conditions we have for the nj's. So nj is rounding up to the next integer of n times aj. So n times aj is larger than nj. And so n times aj divided by nj is less or equal than 1. Okay, now we multiply this expression here with n. So we're looking at n times the variance of stratified estimator with n star repetitions, multiplying this with n. What do we get? So we have now our n here. So we have n times aj squared divided by nj. And if we are using this, so we have n and aj divided by nj, and one aj is left, so this is less than 1, while we just have our aj here and our aj here. Okay, and now we are done, because, well, n times the variance of our stratified estimator is less or equal than this thing here. And this expression we have obtained in step 1. This expression is a lower bound for the variance of the standard estimator, so we can now use this and have shown, if we divide here now by n, that the variance of the stratified estimator is less or equal than the variance of the standard estimator. Okay, and that is a proof that the variance in proportional allocation is actually reduced. So are there better allocations? And yes, there are, at least theoretically. So given the number of repetitions, given the strata, one can do a Lagrange minimization procedure to obtain the optimal allocation here. So the nj's are given by rounding up to the next integer of this expression here. So it's n, the input n, times alpha j times the standard deviation of f of xj, and here we divide by the sum over all of the j's times the standard deviations of the f of xj's. So these are the theoretically optimal nj's given n and the strata. But of course this optimal nj is in general unknown, so here we have the variance of f of xj. If we know the variance of f of xj, we typically know the expectation of f of xj, and if we know the expectation of f of xj, well, then we know the expectation of f of x. So these are the theoretically optimal expressions, but well, again, as in control variates, we can approximate these variances here by another Monte Carlo procedure. Okay, so these are the optimal allocations, and I will do this Lagrange minimization procedure on the next slides. So how to sample from the conditional distribution? Well, that's another question. And at least in the one-dimensional case, and if we know the inverse distribution function of the unconditional distribution, well, then there's a way to do it. And for the other cases, well, you have to really look at it case by case. Okay, so what can we do in d equal to 1, and if we know the inverse distribution function of f? Well, then we can draw from this conditional distribution here as follows. That's the conditional distribution of x under the condition that x takes values in the interval a open, b closed. Well, for this conditional distribution, we can write down its inverse distribution function, ig. And this is as follows. So ig of 0 is minus infinity, ig of 1 is b. And for the other cases where y is in the open interval between 0 and 1, so ig of y is given in terms of I of f, and the argument is f of a plus y times f of b minus f of a. Okay. And as I said, in other cases, multidimensional cases, one has really to look at it in detail. But well, as always, one can try, for example, acceptance-rejection sampling. Okay, so now this Lagrange minimization procedure, how this can be done, that's now the question. So here's a small recall on Lagrange minimization. So the aim is here to find the minimum of the function f, which has O as domain of definition and R as target space under the restriction that g of x is equal to 0. So g is another function which gives the restriction for our optimization problem. And here's a theorem which summarizes all we need. So O has to be an open and convex subset of Rd. F is C1 from O to R. G is C1 from O to R. And now we have our minimal point or our candidate for the minimal point, x star. Lambda star, that's our Lagrange multiplier, and x star and lambda star have to satisfy the following. So first of all, well, x star has to fulfill the restriction, so g of x star is equal to 0. Moreover, the gradient of g at x star cannot be 0. Well, that must be excluded. And we need that the gradient of f of x star equals lambda star times the gradients of g of x star. And then we need another function, this curly L here, which is defined from O to R. And curly L is f of x minus lambda star times g of x. So if this curly lambda is convex, then this x star here, which is given by these conditions, is a global minimum of the constraint optimization problem. Well, and why is this curly L here, and why is this condition on the gradient of f and the gradient of g combined with this lambda here? Well, we can write down the Lagrange function for this minimization problem in this form. So curly L is actually the Lagrange function, so f of x minus lambda gx. And then this condition here tells us, okay, x star and lambda star are critical points, or is a critical point of this function. Okay, but to summarize, we need an x star which fulfills the restriction. The gradient of g at this point cannot be 0. We have that the gradient of f at x star equals lambda star times the gradient of g of x star, and if this curly L here is convex, well, then we have found the global minimum of the constraint optimization problem. Okay, let's now use this theorem for our problem. And first we need a bit of rewriting. So what we're actually doing is, well, we minimize this function here. So n1 up to nm is mapped to the sum over the j's, aj squared divided by nj variance of f of xj. And the restriction is that n1 plus n2 and so on plus n capital M equals n. Okay, and here, well, the n's are integers. So, well, we need to now to treat the integers as real numbers xj. That's the first step. And then, because aj and the variance of xj are given, well, we can just use cj as an abbreviation for this. So cj is aj squared times the variance of f of xj for all the j's. And using this rewriting, well, we have a restricted minimization problem of this form. So f of x1 up to xm is given by the sum over the j's is cj divided by xj. That's the function we want to minimize under the restriction given by this g here. So g of x1 up to xm, which should be again a capital M here. This is given by the sum of the xj's minus n. Okay, that's now the rewriting of our initial minimization problem in a form we can treat. Okay, so now let's compute the gradients and all the other stuff. So for this f, if we compute the gradient, we have to look at the partial derivatives with respect to the xi's. Well, and if we look at the first component, at the first partial derivative with respect to x1, so x1 is only in c1 divided by x1, and all the other sum, it does not appear, so we only have to differentiate this. And what do we get? We get minus c1 times x1 to the power minus 2. So it's just differentiating c1 divided by x1. And for all the other components it's the same. So the i's component is ci times xi to the power minus 2 and with a minus. That's the gradient of f. And the gradient of g is also simple because it's just a sum. If we compute the gradient of g, we just get the vectors with all ones. So the partial derivatives of g with respect to xi is 1. Okay, so this is the gradient of f, this is the gradient of g, and now we need to look at this condition, that the gradient of f equals lambda times the gradient of g. And so we have to multiply here lambda and then look at conditions which gives us that all the components are equal, and this is what we get. So xi star is given by the square root of minus 1 divided by lambda star times the square root of c1. Well, if you plug this in, you will directly see, okay, this is the xi, which does the trick. And of course, because we have here minus 1 over lambda star and the square root of it, this lambda star has to be negative. Okay, that's the condition for the xi's. And Well, but we still have our restriction that x star has to fulfill g of x star equals 0. And how can this be done? Well, we still haven't chosen our lambda star. And this condition g of x star equals 0 now gives that, well, the sum over all the xi stars has to be equal to n. That's our boundary condition. Okay, and rewriting this in terms of lambda star, or 1 over lambda star, we are getting this expression for 1 over lambda star. So 1 over lambda star is minus the square here, and here we have n divided by the sum over the square roots of the ci's. Okay, that's just a standard analysis 2 computations, but they are very, very helpful. Okay, so this is our xi star, this is our 1 over lambda star, and plugging everything together we are getting our x star. Because here we have square root of 1 minus lambda star. If we plug this in here, we are getting that x star is n divided by this sum over this of the square roots of the ci's, and now here we have the vector with the square root of the ci's again. Okay, so that's our x star, this is our lambda star. Oh, these are now x star as a candidate for the minimum. So we still need to check whether our curly L is convex, but this is now easy. So our f is convex, so 1 over x is convex, and also this multidimensional analogon is also convex. And G is linear, so it's convex and concave at the same time. And also minus lambda star times G is convex and concave at the same time. Okay, so we have f is convex, this is convex, and the sum of two convex functions is convex. So our x star here is actually the global minimum. Okay, and all what remains to do is now to replace the cj's by aj squared, the variance of f of xj. Okay, and so then we obtain our optimal allocation by this Lagrange minimization procedure. Okay, so a lot of theoretical properties of stratification. So let's now do 2 examples. So our standard examples, our 2 standard running examples. So the first is our integration problem. So x is uniformly distributed on 0, 1. F of x is given by the square root of 1 minus x squared. The target quantity, well, which is known here, but it's a toy problem, is pi over 4. And we have seen sometimes already that the variance of the standard estimator is around 0.05. And which strata to use now? Well, here we just cut everything into equal pieces. So S1 is from 0 to 1 over 3, S2 is from 1 over 3 to 2 over 3, and S3 is just the rest. And because we have the uniform distribution on 0, 1, the AJs are given all by 1 over 3. Okay, and then if we look at the variance of the stratified estimator, and here, well, for simplicity, I'm having always 3n. So if I multiply 3n with the variance of the stratified estimator with 3n repetitions, because 3n is easily dividable by 3, well, then we get a good reduction of the variance. So it's now 0.01 something. So here we have roughly 0.05, and here we have 1/5 of it. And in this computation here, well, what did I use? So if nj is actually equal to n times alpha j, then n times the variance of the stratified of the estimator is actually equal to the sum over the aj's, the variance of f of xj, over all the j's. Okay. So in this integration example, stratification really helps. So in S1, S2, and S3, we have equal numbers of repetition, and that's the good allocation of randomness. Okay, next example, our road system. Well, we want to go from A to B. The tracks are x1, x2, x3, x3, x4, and x5. So we can go in this way, x1 plus x4. x1 plus x3 plus x5, x2 plus x3 plus x4, and x2 plus x5. So these are the ways, and the quickest way is the minimum of all of them. And here we had this probabilistic modeling of the time we need to travel. And let point me out here is that x4 is the part with the possibly longest delay. So I will do now a stratification procedure, and here we have many variables where we could stratify, but I will restrict to stratification of U4 because this is the possible longest delay, and well, it's a bit of a scenario analysis if we try to control the delay here. And the question is, what is the expectation of capital H of x? Okay, so as I said, I only want to do stratification for x4, respectively u4, the longest possible delay. Okay, and here, if I look at x4, x4 can take values between 2 and 8. And now I cut this into several pieces. So from 2 to 3, from 3 to 4, from 4 to 5, and 5 to 8. So here we have in S1, S2, and S3 we have comparably short delays, and in S4 are all the delays longer than 3. So if I compute the corresponding probabilities that x4 takes values in S1, S2, S3, S4, we are getting 1 over 6 for the first 3 starters, and 1/2 for the last stratum. Okay, and here I've written in slight abuse of notation. So here we are doing stratification for x4 only. So formally, well, here we would need to have product of intervals, but in all the other parts and all the other parts of the product, nothing would happen. So it will be always the full range of x1, x2, x3, and x5. Okay, so here we stratified with respect to x4, and what do we get? Well, we get a bit of an improvement. So the standard deviations seem now to stabilize around 0.85, so other methods were a bit better, but it's still an improvement. And of course, one can think of different stratification strategies. And the running time is still less than 1 second for this number of repetitions. So here the input is now 6 times 10 to the power 6, and all the other inputs are also multiple of 6. Well, in this way, one can nicely distribute the number of repetitions to the strata without doing any rounding. Okay, and how did we get the standard deviation here? Well, we are in the case where aj actually equals n of aj, and we have seen that the n times the variance of the stratified estimator can be written in this way. And now we can use this to do this estimation here. So the standard deviation squared is just given by the sum over the j's of aj times the standard deviation squared in each stratum. Okay, and that's how we get this. We are estimating the variance of f of xj by the squared standard deviation, and then we multiply it with aj, sum it up, and that's our estimator here for the standard deviation. Okay, well, that was stratification, and there are many other variance reduction strategies. So for this lecture, I would like to introduce another one, which is important sampling. So important sampling is a bit of a diva, so it can give you really great variance reduction, but it's a bit difficult to handle sometimes. So in the slogans here, push the sampling measure to the important areas. So again, we have the assumption that x has a Lebesgue density, p, as before. So p of x is given by p times lambda d, and well, that's our target quantity. So we still want to compute theta, and theta is the expectation of f of x, and with this density it can be written in this way. Okay, so now let's introduce another density which is strictly positive on the support of our original density, and this new density is called q. Well, since theta is given by the integral over the support of p, f of x, px, we can now insert qx and qx here and qx there. So qx divided by qx, this is 1, because the supports are respected, we can do this. Okay, And now it's written in a particular way, the integral s f of x px qx times qx dx. Well, in this way, it's another expectation. That's the expectation of f of y times p of y divided by q of y. Well, because it's just the standard application of computing the expectation when y has density q. Okay, so now what we have done, well, instead of expectation of f of x, which is theta, well, we want to estimate this expectation here, which is still theta. But instead of x, we have now as input the variable y with a different distribution. So x has density p, y has density q. And this might be helpful. Okay, and that's the main idea. So this is how we get our important sampling estimator. So the notation is MEMSN, EMS for important sampling. And here we have our set I EMS, and set I EMS is f of y, p of y divided by g of y, and the y i's are IID as y. So by construction, it's unbiased because we have just rewritten everything. So it's unbiased, bias-free, and the variance of set IMS is just the variance of f of y, p of y, q of y. Okay, and as always, the question is now, is this variance here smaller than the standard variance? And also, what about the computational cost? So if f is non-negative, well, you can really get a great variance, at least theoretically, namely the variance 0. So let's now look first at the question, what is the optimal important sampling density, q? And let's look, as I said, at the case that f is non-negative, so f is greater or equal than 0. Then we can write down this g star here. G star is f times p, and then standardized by c. While f is non-negative, f times p is a pseudo-density, and c is now the normalization factor. And this g star leads to a zero variance estimator. So let's look at the second moment. So the expectation of f squared of y, p squared of y divided by g squared of y. If we write everything out, because y has density g star, this is just this expression. Well, this g star here and one of these g star here, below the fraction, well, they cancel, so we just have g star. And now let's plug in what is g star. G star is 1 over c times f times p. So this square goes away, this square goes away, this square goes away, this square goes away, and we get a c in front. Okay, now we have c times the integral over s f of x p of x dx. But if you look at the definition of c, well, we have here c times c, and this is just c squared. And if you look again at the definition of c, c is just the quantity which we wanted to compute. So this is just theta. So c squared is theta squared. So the second moment is theta squared. We have to subtract the squared mean, which is again theta squared, so we get a zero variance estimator. But of course, it's not applicable because we need to know what we want to know, namely the c or the theta. Okay, but at least the statement here gives you a hint how good important sampling densities should look like. They should imitate f times p. And as I said, good important sampling densities can decrease the variance drastically, but they can be really hard to find. And there are many, many recipes. Well, this is their own subtopic, but they all require really skillful selection and application. Okay, let's rephrase the statement in a bit more general framework about the optimal important sampling densities. And in general, this important sampling density does not have zero variance, but the optimal important sampling density is still not feasible. Okay, that's the next proposition about the optimal density. So assume that the second moment of f of x is finite. Well, we always need this, otherwise we cannot speak about the variance. And then the optimal important sampling density is given by this expression here. So it's not f. F can now take both signs. So for density, we need now to take the absolute value of f of x, and we have to standardize by the expectation of the absolute value of f of x, so by the first moment of f of x. And the proof is done on the next slides. And as I said, the optimal estimator has not zero variance. In general, ff changes its sign. Okay, and for the proof, we need again Jensen's inequality, now in the general framework. Actually, the Jensen's inequality before was for discrete distributions, and here it is now for general distributions. So assume that the expectation of f of x squared is finite, and then we have that the expectation of f of x squared is less than the expectation of f of x squared. So we can take the square inside and make by this everything larger. That's Jensen's inequality. Okay, and we need this also here. Okay, let's prove now this proposition here, proposition 10.5. Okay, so Q star is the supposed optimal importance sampling density. Q star is absolute value of f times p divided by the first moment of f of x. And y star is a variable with the slipback density. And we will compare the variance of this random variable with the variance of an arbitrary another importance sampling variable. So y is an arbitrary random variable with density q, and the density q satisfies that its support is larger than the support of fp. Remember, so any importance sampling density has to respect the support of p, so it has to be at least as large, and this is fulfilled here. Okay. So, and then we have this computation here. And let's look at the first part and at the last part. What we are having here is theta squared plus the variance of the importance sampling estimator with this density. And here we have theta squared plus the variance of an importance sampling estimator with density q. And if you drop the theta squared, well, what we're having, the variance of the importance sampling estimator with density g star is less or equal than the variance of the importance sampling estimator with density q. And that's what we want to show. Okay. And now let's look at the steps between. So here we have the mean squared plus the variance. The mean squared plus the variance is the second moment. So we have the second moment here, expectation of fy times py divided by g star y star squared. Okay, let's now use the density. So the density of y star is g star. That's why we have this expression, integral over rd, f of x squared p of x squared divided by g of x dx. Okay, let's now plug in the expression for g star of x. G star of x is absolute value of f of x times p of x divided by the expectation of the absolute value of f of x. And what can we do with this now? Well, here we have f of x squared p of x squared divided by absolute value of f of x and p of x. Well, this square goes away and this square goes away, and we have the absolute value. So from here to there, by cancelling out, we get that this expression equals integral over f of x, absolute value, times p of x, and divided by 1 over the expectation of the absolute value of f of x dx. Okay, this here we can take out. So it's 1 over, so it's actually the expectation of the absolute value of f of x. And if we have taken this out, what remains is the integral over absolute value of f of x p of x. But that's again the first moment of f of x, so we are getting the first moment of f of x squared. Okay. Okay. Now let's recall that y is an importance sampling estimator. So what we are having here, if you ignore the squares first, here we have the expectation of the absolute value of f applied to x. And y is an importance sampling important sampling variable, so the expectation of the absolute value of f of x is the same as the expectation of the absolute value of f of y, p of y divided by g of y. So just by construction we have this identity, because y is an important sampling variable for x. Okay, and with the squares the identity still holds. And now we are almost done, because here we have the square outside. Now we can take the square inside with Jensen's inequality, and we have this expression. And this expression here is the second moment of the important sampling estimator with density q. Well, in the second moment we can rewrite as mean squared plus a variance, and we are done. So it's a skillful rewriting, well, of the second moments with the use of Jensen's inequality, and that shows proposition 10.5. So let's now look at a few examples. So here we have the examples where we start from standard normal distributions and changing the mean or the variance. And here we are, well, w of x is p of x divided by q of x. And if you look at the important sampling variables, well, here for example, here we have f, the function which we want to integrate, and then times p divided by q. So here's the optimal estimator, so just ignore the star. So we multiply with p and divide by q. And this p divided by q, well, that's subsumized in this new w. And this new w, well, that's the thing which we need to multiply our initial function f with, and knowing something about this w might help to quantify the impact of the important sampling procedure in this case. Okay, so lemma 10.7, well, as I said, we start from a standard normal distribution, and first we are changing the mean, so from 0 to mu. Then this wx was given by this expression here, that's the exponential of minus mu x plus mu squared half. So that's the w change we need to do. And the expectation of y of wy squared, that's x mu squared. So here you can at least guess a bit what this change in the mean means for the change of the variance. Okay. And the second case, well, we start again from a standard normal distribution, and now we are changing the variance from 1 to sigma squared. Then we are getting this importance sampling factor, let's call it in this way. So w of x is sigma times the exponential minus omega x squared half, and omega is not an element of our sample space, but this omega is just another abbreviation for 1 minus 1 over 2 times sigma squared. Okay, that's our w. And what is the expectation of wy squared? Well, and if sigma squared is greater than 1/2, we get this expression, and otherwise it's infinity. So here you can see, well, why important sampling is a bit difficult. So if you want to compute some function or some functional of a standard, the expectation of some functional of a standard normal random variable, well, you can try to do important sampling, but you cannot make the variance too small. So if you make the variance too small, well, then the second moment of the correction factor may not exist, and this might have really bad consequences for the variance for the important sampling estimators. And if sigma squared is large enough, well, we are getting this factor. So this may be a bit surprising, but it is as it is, and the proof of this, well, this we will do in the exercises. Okay, and well, I always said an important sampling density needs to respect the support of the initial density. So here it is written, important sampling density Q needs to respect the support of P. Let's give an example for this. So let's start with a uniform distribution on 0, 1. and f of x equals x squared, and y is the uniform distribution on 0, 1/2. So somehow it's obvious that this cannot work to use this important sampling variable, but let's figure it out in detail. So the expectation of f of x, well, that's the integral from 0 to 1 x squared dx, that's 1/3. And for this y, well, we can compute the w. So w of y, that's the initial density, p, and that's the important sampling density. Recall that w has to be only defined for the support of the important sampling density. So we have this expression here, and well, we get 1/2 times this indicator function from 0 to 1/2. And now, well, the important sampling estimator, well, would be f of y times w of y, and let's now compute this expectation, and you can see, well, it goes wrong from this support here already. So this is the integral over r y squared w squared qy. So y squared remains, while we plug in our w, our weight, and the density q, well, 1/2 times 2, but doesn't really help because we are only integrating from 0 to 1/2. And so we end up with the integral from 0 1/2 y squared dy, and this is just 1/24 instead of 1/3. So important sampling, the important sampling density q needs to respect the support of p. Okay, and let's finish today's lecture with our two running examples. So the first is again integration. F of x is square root of 1 minus x squared. Target quantity is pi/4. Standard estimator has a variance approximately 0.05. So now we can try many important sampling densities, and let's now shift a bit more density starting from the 0, 1 uniform distribution in 0, 1 to the areas where f is large. Well, f is large where x is a bit smaller, so let's put a bit more density on the first part, so from 0 to 1/2, and a bit less to the second part. So here we are reshuffling with a factor 2 or factor 1/2. So if you look at these two indicator functions and you integrate over it, well, you get 3/4, so we have a factor of 4/3 to make this a density. So as I said, here's a bit more mass in the first half of the unit interval where f is a bit larger. Okay, then from this q we can compute our wy. Well, it's just 1/this, more or less, because we are starting with the uniform density, so w of y is this expression, and our important sampling estimator is f of y times w of y. Okay, and well, if you compute the variance now, well, we get a bit of a reduction. So from instead of 0, 0.5 it's 0.4, and you can see if you add a bit more intervals here, you can reduce it a bit further. Okay. That's our integration problem, and what's happening for our network problem, or for our road network problem. So what's happening for our road system? So here you can try, as I said, or probably as I always say, many things. While here I tried the important sampling densities qi. Qi is given by 1 plus alpha I times x to the power alpha I, and then times the indicator function from 0, 1 open interval. So and here you see if alpha I is 0, then we have our initial case. So then we just have the uniform distribution on 0, 1. If alpha I is positive, then one puts more weight to long delays. And if alpha I is negative, then you put more weight to short delays. And for having a density, alpha I needs to be greater than -1. Okay, this qi has the advantage that you can compute the distribution function explicitly, while it's just x to the power 1 plus alpha I for x between 0 and 1. And you can also write down the pseudo-inverse directly. So one can do important sampling with this density here. Okay, And well, then our important sampling estimator is as always. So ZIS is h of v times w of v. W of v is the weight. H is the initial function which you want to integrate, and w of v, well, is actually w of v1 up to v5, and it's given by the product of the pi's evaluated at vi's divided by qi evaluated at vi. And pi evaluated at vi is the indicator function of 0, 1 evaluated at vi, and qi evaluated at vi is 1 plus alpha I times vi to the power alpha, and then here the inverse and then the product. Okay, that's our weight. And well, as I said, well, we have the distribution function of the vi's and the inverse distribution functions, the pseudo inverse, so we can sample the vi in the following way. So we just sample again IID uniformly on 0, 1, and then we are computing 1 over divided by 1 plus alpha I. Okay. And if we are doing this, we are getting the following numbers. So it's stabilizing at the same estimate for the expectation of capital H of capital X. And the standard deviation is again a bit smaller as in the standard case. So here I tried alpha 1 equal alpha 2 equal alpha 3 equal alpha 4 equal alpha 5 and equal to 0, 0.5. So a bit more weight on long delays. Okay, so we get a bit of a reduction, but as I said, important sampling can be a bit tricky. The running time increased, so by a factor of 7. So this is actually not really useful. Maybe other weights are more helpful, and yeah, but this has to be tried out, or maybe other densities. And if you look at the implementation, at least my implementation, it turns out that the ITM is the costly part here. So that's the bottleneck for this application here. So the variance is decreased, but the running time is increased, and well, that's not what we wanted to have, but it's what we have. It's the way it is. So as I said, important sampling can be tricky, but all the other methods can also be tricky. So you have always to look at the variance and at the cost. Okay, so that's all for today. So the next lecture will be about quasi-Monte Carlo. That's a bit different approach. So we will leave the random approach for computing expectation, but this can be also be really beneficial. And in a way, we also are coming back to our pseudo-random numbers. Okay, but more about this next week, and that's all for today. Thank you.